Welcome, my dear students. Now I am explaining bimolecular collision theory. Topic is bimolecular collision theory. Here, first we need to know bimolecularity. Okay, a reaction which contains only two reactants. Such reaction is what? A bimolecularity reaction. Here, that's why I am given an example. A plus B gives rise to products. Here only two reactants. So this reaction is a what type of bimolecularity type of reaction? Okay. Now I am coming to the theory. According to this theory, the reactant molecules are assumed as hot spheres and collide together to give the products. The reactant species are hot spheres that collide together to give the products. All collisions do not lead to the formation of products. Here two sentences are there. Reactants are collide to give the products, and all the collisions are not lead to the formation of products. After the collisions, products may form or may not be formed. That is the sentence here. Here, the number of collisions per a unit of time is called as collision frequency, that is denoted by capital Z. How many number of collisions are completed in unit? Unit means what? Second, either minute, is called as what? Collision frequency, that is denoted by Z here. Next, the minimum energy is required for the collision is called threshold energy. Very simple. Some energy is needed for occur the collision. That energy is called as what? Threshold energy. Next, the energy to the reactants to reach the threshold energy is called as what? Activation energy. Okay. For reaching the threshold energy, the required energy is what? Activation energy. Here activation energy is equals to threshold energy minus normal energy of the reactants. Okay. Now here by utilizing the threshold energy, the reactants are goes to activated state. At activated state, the reactant molecules are called as activated molecules. Now the activated molecules are involving in the collisions. Such collisions are effective collisions. They are only converted into the products. Okay, simple. Here for the bimolecular collision theory, the rate of reaction here is expressed. K is equals to PZAB into e power of minus EA by RT. Here P is what? Effective collisions, either probability collisions. Z is collision frequency. AB are reactants. E is energy. EA is what? Activation energy. R is universal gas constant. Is temperature. Here this PZAB is written as capital A. So the rate expression for the bimolecular reaction, K is equals to A into e power of minus EA by RT. Here capital A is called as Arrhenius constant. Here, okay. Now one example is required for this bimolecular collision theory. Here the reaction is what? Methyl bromide is reaction with hydroxide ion. This is what a substitution reaction. Instead of the bromide, we have to substitute the hydroxide ion. What will come? Methanol and here bromide are the products. In this reaction, the number of reactants are 2. So this is what type of reaction? Bimolecularity. Okay. This answer is very simple presentation, students. Okay. Thank you. Thank you very much, all of you. Now I am explaining another important question here. That question is differences between order and molecularity and the examples of bi and trimolecularity. Here we need to define order and molecularity. Here now I am defining order. The sum of the powers of the reactants in a rate law is called order. Here we need to sum the powers of reactants in a rate law is called order of the reaction. For suppose I am given an example here. This is rate law for this reaction. H2 power 1 and Cl2 power 1. 1 plus 1, that is what? Second order. Okay, that is what definition. Here the sum of the powers of the reactants in a rate law is called order of the reaction. Next, molecularity definition. The number of the reactant species in a elementary reaction is called as molecularity. Here elementary means what? Single step reaction. Here in the single step, here the number of reactant species are called molecularity. Okay. Now the second difference, here order can be determined experimentally. Experimentally means practically. Here order can be determined experimentally. Then in molecularity, here it is determined theoretically. Theoretically means what? Here from a balancing reaction, the number of reactants here are theoretically taken. So here molecularity can determine theoretically. Next difference, here order may be whole number or fraction negative 0. Here are possibilities of order values. Whole number, fraction negative 0. But molecularity cannot be 0 and cannot be fraction. It is only whole number, and that is also does not exceed than 3. Okay, here are values of order and molecularity. Next difference, this order is applicable for elementary and complex reaction. Here elementary means which takes place in single step. Complex means what? Which contains several steps. Here order is applicable in both the cases, elementary as well as complex. But about the molecularity, here it is applicable for only elementary reaction. Here that's why I am given here elementary is a single step. Okay, when it is exceed than trimolecularity, that reaction lead to complex. Here there was molecularity is not applicable. Now examples are also important for this answer. Here one example, H2 plus Cl2 gives rise to 2HCl. For this rate expression or rate law, rate is directly proportional to H2 power 1 Cl2 power 1, 1 plus 1 second order. Here a second example, 2NO plus O2 gives rise to 2NO2. The number of reactants here NO here power 2, O2 power 1. Their powers sum 2 plus 1. That's why this is here what type of order? Third order. Here the same reaction without the rate law, rate expression. Here 1 plus 1. Here a bimolecularity reaction. Here the number of reactants 2 plus 1 3 trimolecularity reaction. Here this is about what? The differences between order and molecularity, and examples for bimolecular and trimolecular. Thank you. Here now I am explaining another question also, that is what? Effect of catalyst on the kinetics of chemical reaction with suitable diagram. Here we need to define catalyst and explain the influence of catalyst on the chemical reaction. Now catalyst, a substance not involving in the reaction but increase the speed of the chemical reaction is called as what? Catalyst, and this phenomenon is called as what? Catalysis. For suppose I am taking here potassium chloride, which is in the presence of manganese dioxide, form potassium chloride and oxygen. Here only the reactant belongings are formed here. That's why a main mode is what? Catalyst. A substance is not involving in the reaction but increase the speed of the reaction is called as what? Catalyst. This phenomena is called as what? Catalysis. That's why in this reaction manganese dioxide is catalyst. Okay. This substance not involving in the reaction but increase the speed of this chemical reaction. So this is called as what? Catalyst, and this phenomena is called as what? Catalysis. Here this is explained with a diagram. Here in the diagram, here I am given here two cases. Case 1 is a dotted line, case 2 is what? Dark line. Here reactants converted into the products. Here in case 1, here reaction takes place in the presence of catalyst, required a low activation energy and products forms fastly. If the catalyst is present, here the reaction required low activation energy and products forms fastly. In case 2, here this is case 2. Here reaction takes place in absence of catalyst. Here which required high activation energy and products forms fastly. Here what we understood, if the catalyst is present in the reaction which needed low energy and products forms fastly. This kind of presentation is enough. Okay, thank you.